All right, Owls, this is Mr. O with your next set of flip notes. This is going to be sound flip notes, which is going to be in page number 10 in your Wave TOC. Using the sheet I gave you in class, let's go and follow along. First thing we're going to talk about is just sound in general. We already talked in class that it's a wave that's produced by vibrations in a medium. It's a mechanical wave, obviously, so it has to have a medium. And even though it's longitudinal and the energy and the direction go in the same direction, sound travels in matter in all directions. This is why if someone turns around and talks, you can still hear them because sound isn't going to travel in all directions. It's just going in all directions out as a longitudinal wave. Let's go dig a little deeper into sound waves. If you did not know, it's a mechanical wave, and that mechanical wave travels as a longitudinal wave movement. This is really the only longitudinal wave movement you need to know from now until a long time from now, even though you do find them with earthquakes and other things. This is the number one thing you need to know about longitudinal waves. Let's talk about how sound waves are produced. They are produced when vibrating objects push and pull on a medium and then sends the waves in all directions. The pushing and pulling is what you see with compressions and rarefactions. The pushing is when they get pushed together, and then pulling is when they release out, and that happens over and over and over again in one big cycle. And that's what we're going to talk about here. How particles move as energy is transferred through a medium or through a sound wave. Remember, they do move in the direction of the disturbance because they're longitudinal. The particles are compressed together, hence it's a compressional wave or longitudinal wave. And then they spread apart over and over and again in the cycle. That's how longitudinal waves work. That's how sound is. So if you're banging a drum or making noise, that's how the sound is getting from you to whoever's hearing it. Let's talk about how we make sound. There are three things about how the vocal cords work. I'm really going to shorten this up of how the vocal cords work. But simply, air is pushed up from the lungs, and then we force that air through the vocal cords, and the vocal cords in your throat will vibrate. And then the vibrating vocal cords produce sound waves, which is how you are heard to another person. We have sections and parts of the ear. Now, our ears have three sections, and each of those sections have a part. I really generalize it by calling the sections outer ear, middle ear, inner ear. In the outer ear, you have the ear canal, and the eardrum. There is a more scientific word for the ear, but at this level, all you really know, it's the ear. That's the thing you see on the outside of your head. The most important part of that outer ear is the eardrum. Your ear is shaped the way it is to help you catch sound waves. And then it goes to the middle ear, and the middle ear has three bones, and I really emphasize the word has, because if you look at the three bones, it's hammer, anvil, and stirrup. They all start with H, A, and S. So if you remember the middle ear has three bones, you can remember the order of them. And these are the three smallest bones in your body. And then the last part of the ear will go to the inner ear, which is the cochlea, and then it sends it to the auditory nerve. With the ear, and we'll learn about the eye a little bit later in this unit. Both of them end with a nerve because they will send messages to the brain. Now, the cochlea has little hairs in it that interpret what those vibrations are, and then they send that message to the brain via the auditory nerve. Auditory meaning you can hear it, audio. So how we hear sound. There's three things here. Sound waves cause the eardrums to vibrate. Those vibrations travel through those three little bones in the ear to the inner ear, and then those vibrations travel through the cochlea to the auditory nerve and send messages to your brain on what that sound is. Now remember, learning sounds develop over time. Some people, you'll realize when you hear sound for the first time, you have no idea what it is because the message to your brain cannot figure out what that sound is to you. I relate this often to when you move into a new house and you hear a noise for the first time and you think it's spooky, but then you realize, oh, that's just the dryer or that's just the heater kicking on because it's a new sound to you and your brain has to learn that new sound. You have to learn about the effect of material on sound. Remember, denser the material, the faster it travels. So in a solid, it would be the fastest, liquid would be the middle, and then gas would be the slowest. But keep in mind, speed does not mean how well you hear it. You obviously hear things better in a gas. However, they just travel the slowest in a gas. There's an effect on temperature with sound as well. Higher the temperature, the faster it travels. And this goes back to our matter unit, which means when you increase the temperature, the atoms move faster. And they're moving faster, they're spread out, but sound waves need to hit atoms to move forward, which allows the sound waves to hit them faster because they're moving faster. I always talk about, think about if you're in a gym class and there's people on both sides with dodgeballs and they're just throwing dodgeballs, and if there's a lot of them getting thrown really fast, it'd be really hard for you to cross the gym without being hit. However, there's only a couple people throwing dodgeballs very slowly. You can easily avoid them. You in this demonstration or thought would be the person running, and that would be the sound wave. And every time you got hit by a ball, the sound wave would move forward. So the faster and more often those balls are thrown in the gym, the faster you would be able to move if you were a sound wave. And the last part, I believe, in your notes, no, second to last part, is pitch and frequency. Now, pitch is how high or low a sound wave is, and they are related to frequency. So the higher the frequency, you get higher pitch, and lower the frequency, you get lower pitch. Now, oddly, frequencies of sound waves are measured as transverse wave movements. They're not a transverse wave movement, but the machine that registers frequency produces it as a transverse movement, even though it's longitudinal. So pitch is how high or low a sound wave is. And then intensity, I wrote equals amplitude because intensity is the amount of energy a sound wave has. Intense sound can cause hearing damage. We'll talk about different hearing damage and issues with that. And just keep in mind, most hearing loss issues are found with problems in the cochlea. You might see some students that have issues with their ears have a cochlear implant, which is an implant right in the back of their, behind their ears, which activate the little hairs in the cochlea. That's why they're called a cochlear implant, because it's attaching and getting your cochlea issues resolved for them. Either way, these are your sound notes. Have any questions or comments you have written down, and we will talk about them when we get back to class.